Can you hear me?
Yes.
Okay, great. Let me share this. Here we go. Can you see my screen?
Yes, we can.
Okay, so I'm Todd Gamblin. I'm at Lawrence Livermore National Laboratory, and I'm going to talk about the relationship between Spack and E4S, as well as some activities going on between the two projects. And this includes how E4S uses Spack and also how Spack leverages E4S to test its own software stack. So if you look at how HPC software is consumed, users tend to build it themselves. So they've done this manually for a long time. They can do it with Spack. They can do it with another package manager like Conda or EasyBuild. Facilities install and provide software for users, maybe with modules. And then more and more people are starting to use containers. And that's still a very small percentage of jobs, at least according to the stats that I've seen from large facilities, but it's growing. And someone has to install the software in the container. It's not trivial to write that yourself every time for these large codes like Mike showed earlier. And so Spack targets all three of these. We are trying to make a versatile system for enabling software to be used in all of the environments that HPC users care about. It's flexible. You just download it in the simplest use case, and you can install a package. I think people know this. And it has a very large and growing community. So like Mike said, Spack predates E4S and DCP. We started in 2013, I guess. The first release was in 2014, so we've been around for a while. And the usage has grown. We have close to 3,000 users of Spack on the documentation site every month, and over 4,700 software packages in the main line of Spack. And so, E4S is I guess about 250 different packages there that are the ECP, I think 70 or so software products, plus their dependencies. So it's really a curated part of this larger Spack distribution. And many of the ECP or the E4S packages build on contributions from users in Spack. So there's 650 contributors right now, according to GitHub. And you can see that they're from a large number of organizations, and that's grown since we released the tool in 2014. We really started getting usage in 2016. This pink line is Livermore, where we started Spack, and you can see that Livermore is a pretty small share of the package contributions now. There are a lot of contributions coming in from all over the world, from lots of different organizations, mostly at labs and academia, but also some industry contributors too. Spack is parameterized, and I want to emphasize this because I think, Mike said that E4S is like a Linux distribution, and I think that's true. I think the unique thing about E4S and Spack is that it's customizable to your particular environment, which is something that's very important for HPC, in the sense that, I don't think there's one right way to build an HPC package. If you think about sort of the lowest common denominator, like a typical x86 cluster, there are probably some pretty good standard ways to build things, but in many cases, what we're trying to support are the bleeding edge systems where essentially every build is a port. And so we want to have customizability. And so in Spack, you install a package, if you just don't care how it's built, you can say install the package by name. You can provide a version, you can say install with a particular compiler, you can add build options to these things. They're parameters, flags. We have support for specific CPU microarchitectures now, and actually that's being leveraged by other communities like Easy in the EasyBuild community. And all of these constraints can be applied to the packages and their dependencies. So you have a lot of control over the graph. Mike mentioned earlier to build in E4S and in communities like XSDK, you have to adopt a particular build system. You don't actually have to do that for Spack. You can, essentially, the package is just a Python class that looks like this. And I don't want to get too far into the details here, but I mean, this tells you, essentially, there's two parts. There's what configurations are possible. And so that's telling you what versions you can build, what options there are on a build, what the dependencies are, and this one's optional. So when a particular option is enabled, we depend on MPI. When it's disabled, we don't. So it's really describing a space of builds. And then down here, the build recipe, this can be sort of arbitrary Python code. So you don't have to have particular build systems for this. Those are conventions that I think are good ones. that are adopted by communities sort of within Spack, like E4S and XSDK. And so these are the build recipes down here. This is probably familiar to most people. This is just what CMake args should I use depending on the configuration and how should I install. And I mean, it turns out that this particular package probably is using bad practices. It does not have a proper install target in CMake. And so we have to just copy the executable into the binary directory. And that's possible. It's just a script. So you can pretty much do what you want. The core of Spack is this thing that we call the concretizer. It's also a dependency resolver if you're familiar with other package managers. This is really the part that deals with dependency hell. There are human-generated version constraints in all of our packages. And so like if you look at TensorFlow, there are really complex constraints, like it depends on these specific versions of the build tool when it's at particular versions. There are lots of very tight Python dependencies in TensorFlow. And we take all of these things and combine them with constraints from the package consumer. So whoever is using Spack, that includes the command line configuration files, environments, and so on. We merge all those constraints together and solve this sort of NP-hard problem. And we spit out a resolved graph. And that's really what's being built there. That's those dependency graphs that were shown earlier. We currently have a greedy algorithm. We are working very hard to get out a new solver based on SAT and SMT techniques that would be able to solve even more complex constraints. And these are growing. This is not an easy problem to manage in a parameterized way, all the constraints across an ecosystem. And so we're trying to make that more manageable for people. And again, that gets back to the idea that with a Spack package, you're not just getting one configuration that worked for someone. You're getting a template that should make it easy for you to port things to a new system and to do a build that maybe no one's done before. So that's what we're trying to enable, and that's why this is the core of Spack. It's designed to be flexible. We've extended this idea of abstract and concrete package specs to environments, and this is really what E4S is leveraging in Spack. If you think about the commands that I showed earlier, those are showing sort of partially constrained ways to build packages. So we want a specific version for something, but we don't care about the versions of other things. We want particular options for one thing. We don't want options for another, or we don't care about the options for another thing. We've extended that to what we call an environment, which is essentially a group of Spack packages that can be built together. And that looks like this. I mean, at its core, it's just this list of specs. So if you want to install 3 things, you just put them all on different lines like this. You can put constraints on these, and you can include special configuration. And what Spack does is it takes this and it turns it into a concrete build description. And so we call that a lock file. It's a lock file because it locks the configuration in place. If you wanted to reproduce the build, you could take the lock file and go and build it again exactly the same way on the same type of system. Now this is platform specific, so if you wanted to build on another system, you would need to reconcretize this to build a description that's specific to another system, because some of the constraints in the packages can depend on compilers and platform things and stuff like that. This is really the core of software distribution in Spack. We're trying to build on this abstraction to enable a whole lot of different ways to consume software. And so we have Spack stacks, which are sort of an extension of these environments for facilities, where you can essentially take cross products of lists of specs. So if you wanted to build this list of packages with these compilers and these MPI implementations, you can just make a Cartesian product matrix down here and say, build this build matrix. And that's actually what we use to build E4S. And then I'll talk about that a little later. You can take one of these environments, and if you want to just generate a container for your user, you can do that. So if you just want a set of products that would be in one container, you can make a manifest for that. You don't actually need this long container section. Any Spack environment can be turned into a container with just this Spack containerize command. But you can customize how the container is built with some special properties. And then we just spit out a recipe for you that does a multi-stage build. And so this makes it easy for users to build sort of the same stack of software, either on bare metal in their home directory, or they can take the thing and make a reproducible container out of it with the same YAML description. And so that's one of the abstractions we're building on to enable people to consume these things in different ways. If you look at the E4S website, this is sort of how the E4S containers are done. there's a manifest for E4S, and when we install packages into those containers, it's using something like this to put the packages in the container and build them for that environment just the same as it would for a bare metal environment on an HPC system. You don't have to rewrite your packages for different places. The other thing that we do with these environments is we use them to generate continuous integration pipelines. And so we're trying to make it so that essentially any organization can build a build pipeline to maintain a distribution like this. And so you would have, you know, a stack, like I showed earlier. This top part of this YAML description is just a Spack stack. And then down here, there are some descriptions of how these packages up here, when concretized, should map to GitLab runners. And so essentially all this is saying is when you see a spec that's concretized for Ubuntu, then build it in an Ubuntu container. And when you see a spec that's concretized for CentOS down here, build that in a CentOS container. And this matrix expands to this set of packages. It's just one package with one compiler here for 2 OSs. But you could imagine sticking more in here, and that's pretty much what E4S does. It's making one of these build pipelines. Spack has this Spack CI command that we've built in conjunction with Kitware. We've been working on that for Spack itself for a very long time. And that generates this DAG of builds that then, you know, GitLab can go and build automatically. And if you change the environment, so if you tweak something over here, this will just regenerate the builds for you. So like it will take the newly concretized environment, it'll cache what's already been built, and it will build the things that have changed. And that's really nice because essentially you can version your distribution in one of these YAML files and maintain it that way. You basically push to this repo, this subset of Spack packages is then built in a pipeline for you. And the result is binary packages that you can then use to install things from a cache, just like the build pipeline does internally. So it's very versatile the way that the infrastructure is set up. We've added more features to make it easy for users to get on a system and sort of leverage what's already there too. This is a core thing in Spack. We want you to be able to use external packages like the system MPI. We're working on support to enable this kind of thing for Cray systems where it's really important to leverage the programming environment. And so in conjunction with Cray under the El Capitan and the Coral 2 Center of Excellence and the packaging working group, we are basically making it so that Spack can introspect the Cray environment. And so Cray is at, or HPE now, HPE Cray is adding a JSON descriptor to their programming environment that will use a mechanism kind of like this to find all the packages that are there and then allow Spack packages to rely on them. It's more general than that. Any package can really add its own find logic. And so, you know, we have it built in that, you know, CMake can look through your environment and it'll query the version of the CMake that's around, and it'll add that to your external list along with other common packages. So our developers can get on a system and really quickly instantiate a development environment using some of the packages, say in E4S. So if you wanted to build on top of XSDK, you could do this. And you wouldn't have to build a lot of stuff. You can leverage some things that are already installed. And so the way that this really manifests in E4S, I guess manifest is kind of, no pun intended, is that E4S is a Spack manifest. And so in terms of the way that E4S is versioned and built in a repo, there's a file like this with all of the packages in E4S. And so I think this is the 70 or so ST products up here. Some of them are commented out in this build. But this is really the configuration that's necessary to build all the stuff in E4S. You take this, you stick it in a repo, we make a build pipeline out of it, and then the build pipeline populates the build cache with binaries for all these different packages. And so E4S is really, you know, sort of, it's leveraging all of the latest Spack technologies that we've built to enable distribution. It's using the CI pipelines, they're building containers, and they're using, you know, our binary packaging capability too. The binary packaging, by the way, is actually something that we wouldn't have without a very large community, and that was added by Fermilab and CERN to support some of their workflows early on, and it's turned out to be really useful for other things. But we actually didn't implement the initial version of that on the Spack team. That came from contributors, which I think is really helpful. So yeah, users can install these packages. They can install them in their home directory or in a container. Facilities can install them on bare metal or in a container, and facilities can actually have their own module configuration associated with this. So if they want to expose E4S packages in some way that's either integrated or separate from their existing module hierarchy on their system, that's possible. They can put a module configuration in here and Spack will generate the modules. And so again, this one manifest is used to generate configurations for lots of different ways of configuring software, because there are lots of different ways that HPC users can consume software. So again, when Spack installs things, it can either build from source, so you can build the whole thing from source if you want to, or you can install from relocatable binary packages. And this is the part that we've been working pretty hard on, is to get relocatable binaries working. Essentially, any Spack installation can be turned into a binary package, and that can be made available by a file system, a web server, an S3 bucket. The E4S build cache is just an S3 bucket. And the binaries are used where possible. So like Mike said, we have a hash for every build. If the hash matches, we'll pull it from the binary cache. If not, then we'll build it again. And so you can mix and match your own software products with E4S pretty easily. Again, we generate modules, and so you can install from lots of different places and consume it lots of different ways. It's not trivial, the effort that's required for this. And so like the Spack stack is actually constantly evolving. We merge 75 to 100 pull requests per week. Those don't always affect the E4S stack, but we want to ensure that they continue to work for users. And so E4S is sort of a core set of curated Spack packages that we ensure continue to work robustly. We're trying to expand that. We would love to cover all 4,700 packages one day, but we're starting small with just this E4S set. And the binary cache is what keeps that working. We build the E4S pipeline for trusted pull requests to Spack right now. And so we take this manifest, we have it hooked up to gitlab.spack.io, and every time a pull request goes into Spack, we regenerate this pipeline and build the parts that have changed. And that has been extremely helpful for Spack, just having this core distro that's maintained by ECP people, because we have really good confidence that we haven't broken anything in the core Spack now, because we're testing all these packages. And it's a small set of Spack, but I think it's a pretty good set of tests for for whether at least the core of Spack will work. And like I said, we'd like to expand this to more packages. Now the thing is that at the moment for this pull request testing, we are only building out in the cloud, and so this is done in Amazon currently. What we are working on is ways that we could test this stuff in ECP. And so at the moment, if you're a facility within ECP, you can leverage all of this effort in the Spack community over here. All these contributions are coming in by making a pull request. We run the E4S pipeline in Amazon to test that thing. That gets merged into the Spack mainline. And then right now, ECP sites are testing Spack from the develop branch. So basically, they're not testing pull requests, which are potentially untrusted code, because anyone can contribute a pull request. They're testing the stuff that we've reviewed and put into develop. And then if there are issues there, the E4S staff, they can go back and they can submit more pull requests, bug fixes, patches. They can work with the teams on the SDKs and get things back into the Spack mainline, and then they'll test it again. And then, so again, they can submit bug reports back to the actual product teams. And they can even patch packages that don't have to that aren't developed by ECP members. So Spack has packages from all over the place. Both no one and everyone owns those packages. And so if there's something that you need to fix about someone else's tool, you can patch it in the package. You can go and upstream a change to the package itself. You can upstream it into the package's repo, or you can modify it in Spack. There are lots of ways to do that. And so the benefit of having this ecosystem is that you have sort of a middle ground. Like Mike said, this is the effort that goes into a distribution where you can modify how things are built and make sure that they work on HPC systems. Now, what we'd really like to have is to move all of this testing to the pull request level. And how feasible this is sort of up in the air, but there are security challenges and CPU cycle challenges to doing this. But we'd really like to have it so that if you change a Spack package, we actually test it in all the environments that we care about. And so this is where we'd like to have not just E4S, but other software ecosystems working with us, and so that we can test all the different packages in Spack. What you really need for this, though, because pull requests can contain untrusted code, is open test beds. And so like at Livermore, we're setting up some open machines that are not our main machines that users run on, that would just be for testing Spack packages on relevant hardware. And so once we have that open test cluster set up, I think we can do, at least this E4S pipeline at Livermore on a wide range of architectures, which I think will be really cool, because we'll have the stack built for some fairly exotic systems as far as distributions go. And then, other sites can join in. I think we'd like to use this as sort of an example for other HPC sites that need to work with open source. And I mean, the other thing about this is that I think this is becoming necessary, to have this kind of testing for open software. Even our mission critical codes that, 50% or more of their dependencies are open source. And if we can't test our software against the stuff that's in the open source ecosystem as it changes, it's going to be very hard to track things, and our versions will stagnate. That's what the status quo has been for a long time, is people will take dependencies in and they won't update frequently to changes in the dependencies. And so it becomes very hard to upgrade versions in the long term. And so if we can enable CI like this, where the packages are vetted in the open, and then, once a human reviews them and puts them in the main line, with the benefit of knowing that the tests have passed on environments we care about, then I think we have a much better chance of having robust software for our code teams at the labs. And so this is what we're working on. We have working pipelines on develop at Ascent, which is a Summit-like Power 9 Volta system at Oak Ridge. We have these Amazon pipelines for 2 different OSs, and we recently started building for Skylake and for Graviton out in Amazon and testing that out. And so that brings ARM and optimized x86-64 builds into this. And we have pipelines at NERSC, at least for the Haswell partition. We haven't got all the KNL stuff done because we've deprioritized that as NERSC brings up their new GPU machine. And we're trying to build facility engagement to expand these pipelines for EA systems. A lot of this stuff in here, like supporting more compilers, like all the new GPU compilers and One API, SYCL, things like that. This is going to require new functionality in Spack to support the dependency model for those things, because there are a lot of complexities that go into GPU builds that just don't exist for plain old CPU builds. There are runtime libraries like OpenMP and CUDA and things that we have to get right. And we're looking at modeling that stuff in Spack to support these new environments. The E4S pipelines, they can contribute to facility deployments. We would like it if E4S really became sort of the base for facility deployments. Right now, they kind of sit alongside each other, and we're working on, on merging the deployment techniques for E4S and for what facilities have done for years. And that's taking time. But I think, ultimately, if we can get facilities working together on a stack like E4S, that helps everyone, because the facilities get to leverage the effort of other sites that have similar machines. And they don't have to build their own software stack from scratch as they've done for so long. And so this is what we're ultimately working on. And I think, we need Spack at the core of this, because it really needs to be flexible across different architectures the way that you do this. You can't, we're not trying to standardize on one set of builds for one platform. We're really trying to standardize on a set of templated packages that can work across HPC systems so that you can build in new environments easily. So Samir will probably show some examples of this, but I just wanted to show that E4S is not just for facilities. It can accelerate CI for users. And so I think Mike mentioned that one of his users had, effectively 100x or 10 to 100x speed up on his CI. And so because we have these E4S pipelines and they cache builds, some codes have really just started leveraging this in CI on like GitHub, where there are free cycles, but you could never build, the full stack for a giant HPC application there. And because we have these binary caches, you can just install the dependencies like you would from the system package manager, but they're nice HPC packages. And so then you can build code, run tests, merge, and pull requests and repeat this cycle. And you're not redoing the redundant build of your 60 or so dependencies in GitHub, where it would just never finish because you'd run out of time. So this is a huge advantage, I think, for users, especially the way that software is coming to be maintained. We can accelerate container builds the same way. Essentially, the E4S binary cache is designed so that if you have container recipes, you should be able to pull them from the binary cache. And so if you want to containerize an application and there are dependencies in E4S, you can accelerate that build too, using some of the mechanisms I described above, like environments. And then it can be used, like I said, as part of a full facility installation. And this is where things, they get complicated, because the facilities have preferences on how they build things. Some like to build everything from source, some like to build things from binaries. It hasn't been easy to sort of get everyone used to this kind of virtual deployment environment. but it's coming along. And I think, if we're able to do this successfully and we actually have pipelines running at the facilities, many of the builds that the facilities need will already be in binary caches and built optimized for their site. And so for their site deployment, they will be able to do site deployments way faster than they do now. They won't have to build everything from source, and they can just pull from the binary cache, which would be kept up to date with Spack, along with our CI that I described earlier. So if you think about what is E4S, it's a set of packages which are building blocks that can be used either in user installs, facility installs, and in containers. So you can use these in a whole lot of different environments, and they're installed with Spack. That's what E4S is doing. It is a whole bunch of processes to ensure that this keeps working. And so that's the SDKs and all of the human effort that goes into this. It's the CI pipelines and all the tooling behind that. So it's a lot of work, but ultimately it produces this set of versatile building blocks that you can use. And the packages, there are binary packages, and then the whole process of doing this ensures that the source builds are more likely to work. So it's very beneficial for the Spack ecosystem. It's not one big container image. I think that sort of notion has gotten out there because that's one of the things that they promote. But it really is a versatile environment with a set of curated builds. That's the core of E4S, is this human effort and this versatile set of products that you can use in different environments. There are big container images if you want them, but you can also have a small base image and just pull pieces of E4S. So for future work, we're working on adding testing capabilities to Spack and E4S. We are not trying to compete with packages like Reframe, but we'd like to leverage them. And so we're adding the capability to put smoke tests into Spack packages so that you can just Spack install this whole E4S environment and then run Spack test and have all the packages vetted on the machine. And we're trying to do that again in a parameterized way so that the tests are versatile across systems. You don't have to write a test suite for every machine you want to run on. We want to leverage systems like Pavilion 2 and Reframe because those enable more extensive testing. You can do a lot of parallel runs. You can do combinatorial runs and things. And we don't want to reinvent the wheel with that. So we're trying to develop integration that would let you take a Spack environment and farm out tests to something like Pavilion or Reframe. And then we have a new ECP project that's built around this. We want to leverage these capabilities to test the Shasta systems and to merge this E4S test suite that's currently, it's in its own repo. It's not merged with the Spack packages and it requires some maintenance. We want to reduce the maintenance by essentially parameterizing those tests and merging them with Spack packages. So we're working with facilities to expand all of these different environments where E4S is used and to test the stack on new early access Shasta systems as the exascale machines get closer and closer. We're looking at adding security measures directly to Spack. So we are looking actually at Livermore into adding things like virus total or scanning on every package merged into Spack so that we can have more assurance even at like the SecOps level in addition to just does it build. That's something that I think we can work into CI that we're trying to do. And then I said earlier that one of the things that will be challenging as we move on to these new systems is really the compiler ecosystem and the runtime ecosystem for GPUs. We have the first prototype of Spack running where we've made compilers into proper dependencies and we're modeling things down to runtime libraries like libstdc++. And I think that will be a big deal as we move into environments where we have to do mixed compiler builds and we have to use different GPU runtimes and different dependencies are using different GPU runtimes. Merging all of that together, that's the dependency hell we're trying to target. And so this is the first step towards that, towards actually modeling that ecosystem and managing the kinds of constraints that are on it. So that's it. I hope that gives you a better idea of how Spack and E4S are related.
Thank you very much, Todd. If you could take some time and answer the questions in the chat window, we can move on to the next talk.
Okay.